Hi, welcome back. So the next section we're going to look at is ATA 21, air conditioning. So first thing to say is we've got two air conditioning packs that are fed with air from either of the two engines or the APU. So a couple of things worthy of mention at this stage before we delve into the details. So the air conditioning pack has certain protection features built into it, so that if we have an over temperature situation or an over pressure situation, that will cause the pack to shut down. Also, the packs have two modes of operation. There's a normal mode which delivers a normal flow rate, and a higher mode or a high flow rate. That's not controlled by the pilots at all, it's controlled by logic. And the basic logic in a nutshell is if we have a single pack operation, because the other pack has either been turned off by the crew or it has failed for whatever reason, probably an over temp or an over pressure situation, then the remaining pack will ramp up to deliver a higher flow rate to somewhat compensate for the loss of air from the failed or switched off pack. There is further protection built into this, so that if the pack starts to overheat, but before it reaches the over temp threshold, which would cause the pack to shut down, before it reaches that, a relay will operate, and what will happen is the pack will then ramp down to the lower flow rate, the normal flow rate. The other thing, some other logic that's built in, so during engine starting, depending on whether it's an engine start or an APU start, the packs are shut down during engine start and then come back online. During a max power takeoff using takeoff 1 thrust rating, the packs, both of them, will automatically switch off during the takeoff run. In that situation, the pack requires a reset from the crew, or the packs will require a reset for the crew. Well, bear in mind, there's a couple of ways around this. One, that doesn't happen if the crew are using the APU to supply the packs during the takeoff run, which they can do. You can have the APU running and the engines running. And if you configure it properly, you can have the APU supplying the packs, and then the engine air, we're not going to take any engine air off the engine, so as far as the fader is concerned, he's perfectly happy. So the packs will not shut down in that situation. But if they are taken off using engine air as a source of air, and is in the takeoff rating, the takeoff 1 rating I should say, which is a high power rating, the max power takeoff, then both packs will shut down. The crew will then have to reset the switches after they've gone through the takeoff phase. Now all of that, the protection and this on-off logic during starting, during max takeoff, it's all controlled not by a computer, not digitally, but by relays in the system. Just hardwired relays. So the logic is all relay logic. So there's a ton of relays in the system. And that's actually worth bearing in mind when it comes to troubleshooting. If one of these relays are not working, then it's going to cause problems. The system's not going to work properly. Maybe the pack will not go online, or it won't go offline when you expect it to. So just bearing in mind, it's obviously when you're troubleshooting, spend a little time troubleshooting, look at these relays, ask yourself, is it possible that one of these relays is not working? Because it's a lot cheaper and quicker to replace a relay than it is to replace a pack valve or whatever it is, cold air unit, or whatever it is you want to replace. So what we'll do now, we'll go over to the PowerPoint presentation and we'll go through all of this, and I'll see you on the other side. Okay guys, so let's take a look at this first slide. Actually this slide is from chapter 36. What I've done is I've combined chapter 21 and 36 together. It's a little bit easier. So what we can see here is the bleed sources. If we take a look at the engine, there are two bleed systems. We have two engines. Only the left-hand one is shown. The right-hand one is identical. So what we can see here, we can see the two bleed ports on the engine, LP stage 9 and HP stage 14. If we take a look at the LP stage 9 first, that comes off the engine through a bleed air check valve and then passes through the pylon, through a pre-cooler to the engine bleed valve. The 14 stage air, if we take a look at that, First thing to note actually is the air comes off the 14th stage and is tapped off directly and is made available for the engine anti-ice system. So what we can see from here is the engine anti-ice system uses only 14th stage air, and it's available regardless of the status of the actual engine bleed valve itself. The engine bleed valve is controlled by the pilots. They can turn it on and off. But even if they turn it off, there's 14th stage air available to the engine anti-ice system, as long as, of course, if the engine is running. The other thing to point out is this air for the engine anti-ice system, its only source is the on-side engine. You cannot use the APU air, you cannot use the other engine's air to supply it. There's nowhere the air can get to it from another source. So the air comes off the 14th stage, passes through a high stage valve. This is controlled automatically by the system. And what we have is a high stage pressure switch. And we're going to use HP 14th stage air when basically LP 9th stage air is not going to be sufficient. So always bear in mind 14th stage air is always going to be a higher pressure, higher temperature than 9th stage air. So when the engine's turning at low RPM, 9th stage air might not be sufficient. So in this case, we're going to open up the high stage valve and we're going to use 14th stage air. The 14th stage air will pass through the 14th stage check valve, comes down to basically a T-piece, and will follow the line down to the LP 9 stage check valve and basically block it off. The 14th stage air pressure is always higher than 9th stage air. It's going to win, it's going to block off the 9th stage air and force in the bleed air to be the 14th stage air that's available to the airframe. So what controls a high stage valve? Well, it's a high stage pressure switch. So we're going to base whether the high stage valve is open or closed based on the pressure coming off the 14th stage air. If the 14th stage air pressure is less than 46 psi, that means 9th stage air is even lower, and we're going to use it. We're going to use 14th stage air. Once 14th stage air pressure builds up, as the engine accelerates, once 14th stage air pressure goes above 46 psi, the pressure switch operates, causes a high stage valve to close, and then it just swaps over now and uses the 9th stage air. So the air, whether it's coming from the 9th stage or the 14th stage air, comes along and passes into the pylon where there's a pre-cooler. Now the pre-cooler uses fan air to cool as a cooling medium. Controlled, or the flow of that cooling air is controlled by the fan air valve. Now in the picture there it's showing a fan air control thermostat. It's just a line pointing to the pipe. It doesn't actually show the valve. And in actual fact, this is an old picture. The fan air control thermostat is not located in the pylon anymore. It's under the cabin, beg your pardon, under the cargo compartment floor. But the fan air control thermostat is purely a pneumatic thing. It's no electrics involved. And basically it's going to modulate the fan air valve. And what we're aiming for is a temperature, a bleed air temperature downstream of the pre-cooler of around 200 degrees C. If the bleed temperature rises, the fan air valve opens up a little bit more, allows more fan air, cooling air to come through, bleed air temperature will drop. So it just modulates that fan air valve so that downstream of the pre-cooler, we've got approximately 200 degrees C. The air then comes to the engine bleed valve. The engine bleed valve is controlled by the pilot from the control panel, the bleed control panel, using the bleed switches. These valves are either energized or de-energized. When they're energized, they're open. When it's de-energized, it closes. And if we open it, the air then is then available to our air conditioning, pressurization system, and to operate the wing anti-ice system. We also have an APU bleed valve to supply, for APU bleed air to supply the system. A cross bleed valve, which is normally closed, but it is there to, if we've only got a single bleed available, we can open up the cross bleed valve and it can feed the other air conditioning pack and operate the wing anti-ice system on that side. those three circles, which are highlighted now, they are massive leak detectors. Massive in the sense of a huge leak, not physically the detectors themselves are massive. And they will cause the respective bleed. There's three of them, one for the APU, one for the left bleed, one for the right bleed. They will cause the respective bleed system, be it left, right or APU, to shut down in the event of a huge leak in a critical area. The cross bleed valve, which is normally closed, if it was open, the massive leak will cause the cross bleed valve to close, because we don't want the bleed air to feed a leak that we're trying to isolate. Now, there are a whole bunch of other leak detectors in the system which are all the same. In terms of physically, they're all the same. There's loads of them. I'll show you a picture shortly. They will not cause the bleed valve or the bleed system to shut down. They merely generate a leak message. But those three massive leak ones, they will cause the bleed system to shut down. Okay, so let's just take a look at the next slide where we can see some component locations. Okay, this picture then shows you where these high stage valve is located. So you can see here the high stage valve. You can see the high stage pressure switch. I'm just highlighting these to you now on the PowerPoint picture. You can see the HP port and the LP9 port, those two pipes. And you can see from the HP port, the air goes off to the high stage valve. But then just prior to that, it goes forward. And that other valve you can see here as the pipe goes forward is the engine anti-ice valve. Okay, this picture we can see our air conditioning control panel. What we're concentrating on here is at the bottom of the panel. So you can see bleed 1, bleed 2 switches, the APU bleed switch, and the rotary switch cross bleed, which is auto, open or closed. So just take a look at the bleed 1 switch first. So here we can see if there was a leak from one of those other leak detectors, a leak light will illuminate. As long as it's not a massive leak, if it was a massive leak, the bleed system will shut down. But if it's just a leak from somewhere else, the leak light will show, and it's up to the crew to decide what to do. Normally the switch is black, completely black. If you push the switch and release the button, you get a white striped bar in the switch. The engine bleed valve is de-energized, and that's the engine bleed valve is now closed. Pushing the switch, the white striped bar disappears. Power supply goes to energize the bleed valve, and the bleed valve will open. For the APU bleed, when you switch it on, you get an open inscription. If you push the switch to release it, the open light comes off, and the bleed valve will shut. Is energized, de-energized in the same way. Bleed 2 switch is the same as bleed 1. And then the cross bleed switch. We've got auto, closed and open. If you put it to the closed position, it will never open. It will always be closed. If you put it in the auto position, it opens up automatically. If you've turned on both air conditioning packs, for example, and you've only got one engine bleed, then the system just says, well, okay, he wants both packs on. I have to open the cross bleed valve in order to get the air supply from the other side. It will do that, of course, as long as there's no massive leak. If you go to the open position, the bleed valve will open. Again, though, if there's a massive leak, it won't. Also in the auto position, when you're doing engine starting, depending on which engine you're starting and the situation, but the cross bleed valve will open to supply air for the engine start system. So for engine starting, the crew don't really need to worry about configuring the bleed system, because the system will do it automatically. The other switches, the pack switches, gaspers, and the temperature control and the recirc, we'll talk about that a little bit later when we do the air conditioning bit. So this picture on the MFD, on the synoptic page, and with, as you are well aware, the synoptics on the Embraer 145 are pretty basic. So this is the ECS synoptic page, for want of a better word, but synoptics is probably over-egging the pudding somewhat. All you get on the ECS page is cabin and cockpit temperature, as you can see, and an indication of bleed temperature. And it doesn't even tell you how many degrees. You've just got the sort of sliding scale there with the 2 arrows for the left and right bleed. Should be in the green. If it does go in the red, that means there's a leak, and you'll have the respective leak message if that happens. I do apologise. That's false. Ignore that. A leak is a leak. This is talking about bleed temp. This is the actual bleed temperature. So if it goes in the red, I apologise, you get a bleed over temp message, not a bleed leak. A leak is something completely different. Wow, here we go. Well, this looks like a complete nightmare, but actually it's not. What this picture shows is all of those leak detectors I was talking about. Remember I said there's the 3 massive leaks, but then there's a whole load of others, and this is all of them. They're all basically thermal switches in parallel, and if any one of them detect a leak, basically there's a ground signal and the system knows there's a leak somewhere. It does not tell you where the leak is other than left side or right side. That is one of the, this is sort of first generation glass cockpit aircraft. It's not the latest things. It's not smart. They're just literally thermal switches. I think there's about 26 of them on each side in each system. So if there is a leak, you'll get a leak message. If it's a massive leak, it will shut down the bleed system. But then it's down to taking all the panels off and physically trying to see where the leak is coming from, because you've got no way of telling. They're all in parallel. You've got no way of telling which one is leaking or which one is indicating a leak. Okay, so here is the distribution system. So ECU is Environmental Control Unit. We're going to talk about that shortly. That's basically the air conditioning packs. But the air exiting the air conditioning packs leaves the ECU and joins into the distribution ducts inside the cabin, following the yellow line there from each pack. And basically what we have is upper ducts, lower ducts, and gasper. The gasper ducts, which is the white one, the one that's not coloured in. The control, whether the air comes out the upper ducts or the lower ducts, that's controlled by that 3-way valve and a thermal switch. What the thermal switch is looking at is basically a temperature of the duct air. So if the air in the duct is 24 degrees C, remember this is conditioned air now, if the air in the duct is more than 24 degrees C, in other words warm air, then the 3-way valve will operate and the majority of the air will be pushed down the lower ducts. So you get nice warm air out around your feet area. If the temperature is below 24 degrees, there's a bias towards the upper ducts. So a little motor moves and it operates a 3-way valve and the air is pushed out of the upper ducts. So you get nice cool air coming out of the upper ducts. You've also got the gasper ducts, which is the one that's not coloured in. That air is coming from the output of the ECU, plus also recirculated air, and you can see a little fan there, that's a gasper fan, which the pilots can turn on and off. Now the gasper duct, so there's 2 little circles there on each seat area basically. They're the little louvres that the passengers can adjust in the PSU. But you'll also notice there's a pipe goes off to the right of the picture. That actually goes into the rear avionics compartment and provides cooling air for the rear avionics compartment. So when you're on the ground, got ground power on, the gasper fan runs continuously and you cannot turn it off because it provides a cooling air for the equipment in the rear avionics compartment. Now just take a look forward on the left hand side of the picture. So from the ECU, you've got the yellow pipe, the 2 yellow pipes, and one of them, the lower one, there's a pipe that's not coloured in, it's a white pipe, it goes all the way along and disappears off the left of the picture. That's the air going towards the flight deck. So what we can say from here, the left-hand pack predominantly does the flight deck, the right-hand pack predominantly does the passenger cabin. There's no valve that controls that distribution as such. It's just the diameter of the pipework makes it work. So basically, for the left pack, 60% of the air goes to the cockpit, 40% to the cabin. Okay, so that's that. So that's a distribution system. Okay, so let's just take a look at, we're going to talk about the air conditioning packs now. So let's pick up from, if you remember from the, right at the beginning, the intro, I said there's some logic going on. So let's take a look at this logic. So first of all, some things to bear in mind. So these are some of the rules that the logic operates to. So first of all, both packs will close during max takeoff power using the takeoff 1 rating, and a pilot reset is required. Second rule, during engine start using APU air, both packs will close automatically, and after the engine start, they automatically come back on stream. Second one, during engine start, if you're using bleed air, the pack of the engine being started will close. The pack of the engine being started will close. The other pack, if it was on, carries on. Again, auto reset. So everything goes back to normal once the start cycle's finished. And finally, I didn't mention this right at the very beginning, but pack 1 will close if we're in icing conditions below 24,000 feet. Again, auto reset. So once we leave icing conditions, the pack 1 will come back online. That's, of course, only if number 2 pack is working at the time. The system will never shut down pack 1 in this situation if number 2 pack wasn't working, because obviously we're using the pack air to pressurize the cabin, and that would be bad news if we shut it down. Okay, so let's go through the air conditioning pack. We have 2 of these packs. They're both the same, although the logic is very slightly different, because of the icing condition thing we just mentioned just now. But the packs themselves are identical. So let's take a look what we've got. Well, first of all, this is showing the left pack. We can see at the top picture, we've got our left bleed supply coming in, and the first thing it hits is the pack valve. Now the pack valve, like the engine bleed valve, is a solenoid operated valve. It's energized to open it, de-energizes, it will close. It uses air as muscle air to open and physically open, and spring-loaded. If there was no electrical signal or no air, it would close. There's actually 2 solenoids on the pack valve. You've basically got your on-off solenoid, and you've got something called the set-down solenoid. Okay, I'll talk about the set-down solenoid in a minute. So turn on the pack using the pack switch. It energizes the pack valve. The pack valve will open and allows the air from the bleed system to come down. The first thing downstream of the pack valve is a pack overpressure switch. That's set to 55 psi. Now the pack valve it regulates the pressure to either 34 psi in normal flow or 43 psi in higher flow. So normally it would be 34. But if the pressure should, for whatever reason, end up at 55 psi, the pack overpressure switch would operate, and that will cause the pack to shut down, and it stays shut down until the pack or until the crew reset it. But all being well, the air will then come down, and the next thing it comes to is this dual temp control valve. So what you see here is 2 valves, 2 physical valves, but actually 1 unit, controlled from a single torque motor. This is our temp control valve. And you can see in the picture there's 2 valves, it would appear to be, but as I said, they are mechanically joined together, so when one valve opens, the other valve will close. Let's take the easy route first. If we follow the line straight down, this is the hot air stream. The air conditioning pack components are all completely bypassed, and that hot air comes down straight down through a mixing chamber where it mixes with the output from the cold air unit and goes into the cabin. So easy peasy. If we follow the cold cycle, so the air comes down to that junction and goes to the right as you look at the picture, and it passes through the primary heat exchanger. The primary heat exchanger is using ram air to cool it down as a cooling medium. Passes through the primary heat exchanger where it cools down from the ram air effect, and it then comes to the cold air unit, which is a compressor and a turbine on a common shaft, and actually on that shaft there's also a cooling fan that draws air across the heat exchangers when the aircraft's stationary and on the ground. Otherwise there would be no ram air as such. So the air conditioning system works pretty well actually on the ground when it's stationary on the ramp. So it passes through the compressor. Now the compressor is going to compress the air, so that means the temperature is going to rise and the pressure is going to rise as well. So temperature increases, which seems a bit of an odd thing to do as we want to cool it down, but it just makes the whole system work. There are two switches, two protection switches now, overtemp switches. There's the pack overtemp switch and the pack set down switch. We'll talk about the overtemp first. That's set to 243 degrees C, and if the temperature leaving the compressor gets to 243 degrees C, it will cause the pack to shut down, and once it's shut down it's latched. The crew would have to reset it on the switch. The set down switch, I'll talk about that in a minute. So it then comes and makes another pass through, this time the secondary heat exchanger. So we're going to, again, ram air is going to cool it down. Comes out of there, passes down to a condenser, which is another form of heat exchanger really, except the air going through the core of the condenser is the air that's actually coming out of the whole air cycle machine. And the air going through the condenser, any liquid or moisture in the air, it will condense. That's its job. It causes the moisture in the air to condense into a liquid, and that liquid is collected in the water collector. And then through some swell vanes, that water is flung out by centrifugal action and out down a hose pipe, and is actually squirted across the heat exchangers, which makes the heat exchangers work much more efficiently. So we've now got nice dry air that's been cooled from the secondary heat exchanger, although there's still a lot of thermal energy there. You certainly wouldn't want to touch it with your hands, it would be really hot. And it then comes to a turbine. Now the turbine, we're going to make the air do work. That means it's going to give up its heat energy. We're also going to expand it and reduce the pressure, so that means the temperature will also drop. So the temperature will drop through expansion, pressure reduction, and by making it do work. By the work that it does is driving the compressor and the fan. So when it leaves the turbine, it's cold. At altitude, that can be really cold, maybe 3 degrees C, something like that. The air will then mix with the hot air that's come down from the temp control valve. And by the way, even if you're fully cold, even if the temp control valve's in the fully cold position, you're still going to get some air going through the warm, the hot bit. And likewise, if you've gone fully hot, you're still going to get some air flowing through the heat exchangers and driving the cold air unit and so on. So it doesn't completely block off. So it mixes with air coming through there, from there, through the mixer, through the core of the condenser, into the cabin, or back into the cabin. Now, underneath the cabin floor, there are 2 recirc fans, one for each pack. The crew can turn those on and off as well, and that recycles the air from under the cabin floor area and basically just recycles it. So the air is drawn from under the cabin floor, some of it's recycled. So basically it reduces the airflow coming off the engine, just a little bit better from a fuel efficiency point of view. Okay, so we said about this set down switch. So the 2 temperature switches after the compressor, the overtemp one, we talked about that, 243 degrees, causes the pack to shut down. The other one is the set down switch. That's set to a lower temperature. Now, what we said earlier on is the pack can operate at 2 flow rates, 34 psi or 43 psi. When does it go to 43 psi? Well, basically, if the other engine is shut down, I beg your pardon, if the other pack is shut down, either because it's failed or because you've turned it off. If you've only got one pack running, that pack will run at high flow mode. Now, if you've got a cold temperature selected, you're going to be pumping a lot of air through that air conditioning, the cold air unit, the air cycle machine. That compressor is going to be working hard. Everyone's going to be working hard. Possibly, you will have, you could end up with a situation where you start to get into an over temp situation. Now, we know at 243 degrees C, we know that the pack will shut down. We don't want that to happen. If this is going at high flow mode, that means the other pack is not working. What we don't want is to shut this one down. So there's a set down switch. It's set to a lower temperature. It's set to 221 degrees C. What that will do is send an electrical signal to the pack valve, and it goes back, it resets it to the normal flow mode. Hopefully that will take the heat off, excuse the pun, the air cycle machine, and it won't overheat and trip. There is another temperature switch. Actually, there's a temperature switch just as the air comes through the mixer, through the core of the condenser before it goes into the cabin. There's another temp switch there. It's measuring the duct temperature at that point. The temperature is 90 degrees C. That will actually also cause the pack to shut down. You also see where the heat exchanger duct is. At the top there, you've got the ram air valve. That solid blue line there, that dark blue line. If the ram air valve opens, which is basically like a flap, comes down, blocks off the airflow to the heat exchangers, and diverts all the air through a check valve and into the cabin or cockpit stroke cabin duct. And basically fresh air, ram air, is ventilated into the cabin. That ram air flap is controlled by an electrical actuator. Again, you'll notice on the control panel, there's no ram air switch or anything like that. The logic is automatic. If we're in flight and both air conditioning packs are not working, either because they're switched off or because they've failed, then the ram air system automatically operates. The flap is actuated to the down position, and the ram air is now ducted into the cabin. And as long as the ram air pressure is higher than cabin pressure, it can overcome the check valve and you'll get fresh ram air into the cabin. So that's basically it for how the pack works, how it cools down. The controls on the air conditioning pneumatic control panel. So we talked about the bleed switches earlier. Just above that, then you've got pack 1, pack 2, and the gasper switch in the middle. Everything, dark cockpit. So when everything is switched on, everything is good. Dark switch, nothing is shown. If you turn the pack and release the switch, you get a white stripe bar. That means the pack is not working. And that's what you have to do to reset it if you have a trip. The recirculation fan is on or off. The fan itself has 2 speeds, but that's based on duct temperature, but we can turn it on or off. Again, white stripe bar means it's switched on. Then you've got the 2 rotary switches for the temperature control. One for the cockpit, one for the cabin. And you notice the cabin one has got hot, cold, C and H. And if you turn it to C and then click it a bit more, it goes to the attendant position. And what you do there is you hand over temperature control for the cabin over to the flight attendant. And the flight attendant has a control panel where she can adjust the cabin temperature control. The cabin temperature system has 2 modes of operation, automatic or manual. Normally it's in auto mode. If you want to operate it in manual mode, you pull the knob, it clicks, and you can rotate it hot or cold. And now you're operating the system in manual mode. But we'll talk a little talk more about that later on. Okay, this picture again looks like a bit of a nightmare, but it's not, and I'm not going to go through every relay. It's really hard to do it unless I'm in the classroom in front of you pointing to the individual relays. So what I just want to highlight here is the fact that all of this control about switching the packs off if they overheat and so on is all done by relay logic. First of all, to mention, so the pack valve itself, what we're looking to control is down on the bottom right hand part of the picture, in the bottom right hand corner. And you'll see there are two solenoids on there and they share a common ground. One is basically the on-off solenoid, that's the one on the solenoid that was on the left. And the other one, it says high stage solenoid, that's the solenoid that causes it to go to the high stage mode or the high flow mode. The high flow mode solenoid, if it's energized, it goes to high flow mode. If it's de-energized, it goes to low flow mode. The other thing to point out is the power supply. So in the middle of the picture at the very top, you'll see a buzz bar and it says DC buzz 1. This is for the control of pack 1. Pack 2 control is similar, but it's off the DC buzz 1. And the packs are either energized, de-energized. What we said is if it's de-energized, it's off. If it's energized, it's on. So that means the implication here is on the DC buzz. That means in an electrical emergency, we will lose both air conditioning packs. They will not be available. Now, down on, there's an area that I'm going to highlight on the screen for you with 5 relays. I'm just highlighting them now. These relays are linked into the pressure switches, the temperatures, the over temperature switches, and the FADEX. Plus there's one for the APU. The one on the far left is the APU one. So the first 2 relays that we are going to look at in the picture, the ones on the left hand side, so you've got the APU one and then you've got 2 more relays next to each other. They're both, if you follow it down, they go to the FADEX. What I would say, any of these relays, apart from the APU one, forget about the APU one for now, but any of the other relays, if they are energized, you can follow it through yourself, but if they are energized, the pack will not work. So in order for the pack to come online, in order to get power to the pack on the solenoid, all of those 4 relays have to be energized. Have to be de-energized, like they're shown in the picture. In the picture, they're all de-energized. Okay, so forget about the APU one just for now. But the other one, the other first 2, they're linked into the FADEX. So this is what causes the pack to shut down if we're in the takeoff 1 rating. The FADEC knows what rating we're in. The relays don't. So the FADEC is in charge of those 2 relays, and if we're in takeoff 1 and we advance the power levers, when we get to the takeoff position, the FADEC will provide a ground signal to these relays, and the relays will these relays will energize. Now we've got 2 FADECs there. It depends on which FADEC's in control of the engine at the time, and it doesn't matter because all these contacts are all in series. So whichever FADEC it is, be it the, let's say it was FADEC 1A, which is the first box, when we advance the power levers and we're in takeoff 1, the FADEC will provide a ground signal causing that relay to energize. That means the pack will shut down. There's no more power going to the on solenoid. It de-energizes and it shuts. Of course, if we're using the APU air, that's not going to happen. We don't need to shut the pack down if we're using APU air as our source of air. So just the first relay then, the APU bleed relay, that will be energized if the APU bleed is on. So that means the FADEC can do what he wants. He can provide a ground signal, but there's no power going to the relay. So there's no power at X1 of that first FADEC relay if the APU is online and supplying the air. So that means there's no power to X1, so there's no ground signal, therefore it doesn't energize. So the packs will continue. So that's the first. You've got the pack shut-off relay number 1, that's controlled by FADEC 1A. You've got pack relay shut-off number 2, that's controlled by FADEC B. So that does the pack off when we are in takeoff mode. The next 2 relays are to do with overpressure, the 243 degrees C temperature switch. That controls pack shut-off relay number 3. If we're in an overtemp situation at the compressor outlet, 243 degrees C. Or the overpressure one, 55 psi. That controls actually that same relay as well. So that relay there, pack relay 3, can be energized by either the overtemp situation or an overpressure situation. And also a latching circuit is formed between contacts A2 and A1. So once that relay is energized, it will remain energized, and the only way to stop it is to switch the pack off, and that will release that latch. So what we can take away from there is, if we have an overpressure condition, an over temperature condition, the pack shuts down and it stays shut down. The crew have to reset. Actually, same with the FADEC. If you look at relays 1 and 2, a latching circuit is formed again with contacts A1 and A2 on the relay itself. So the crew have to do a reset on the pack. The other relay, relay number 4, is basically linked into the engine start system. So what we said is during engine start, if we're using APU air, both packs shut down. If we're using the engine to start the other engine and the engine that's being started, the pack shuts down. That's basically being controlled by relay number 4. It gives you the logic in that little box there as to when it energizes or not. There's no latching circuit, so once the start cycle is finished, it goes back to normal. It just resets, and then the pack will come back online. So just above there, we've got K0529, which is pack 1 shut-off relay number 5. If you follow that, that goes to the air data computers. Ground is provided to that relay if we're greater than 24,000 feet. You think, well, why do we do that? Well, it's all linked into the next relay along. I'm looking at the number there, K0435, wing anti-ice valve relay. So if we're in icing conditions, what we said is, if we're below 24,000 feet and we're in icing conditions, the pack will shut down. Pack 1 shuts down as long as pack 2 is running. So that wing anti-ice relay is going to operate whether in icing conditions or not. And then the other relay that's sort of linked into it is the air data controlled relay, which is going to energize or de-energize whether just purely based on altitude. So one's purely based on icing conditions, one's purely based on altitude and nothing else, and they're not talking to each other. But through the wiring logic, it will determine whether the pack closes or opens. So below 24,000 feet and in icing condition, it closes. If we're in icing conditions but we're above 24,000 feet, it stays open. Now the high stage solenoid, again, you'll have to trace this through yourself, but what we said with the high stage valve is if the other pack's not working, so in this case this is pack 1, so if pack 2 is not working, the high stage solenoid will energize. So we've got, it says pack valve 2 position relay number 2, just on the right hand side of the picture there, about halfway in the middle of the screen, slightly to the right. It's shown in the de-energized state. So this is the position it's in if pack number 2 was not working. And basically there's a, if you trace it, it allows electrical power to come down to the high stage solenoid, causing it to energize. But if pack 2 was online, it would stop that from happening. Up at the top right hand side of the picture, you've got another temperature switch. That's the that's basically the set down switch, 221 degrees C. So if we go above 221 degrees C, it causes the pack 1 set down relay to energize. When that energizes, it interrupts the power to the high stage solenoid. That causes the pack to go to low flow mode or normal flow mode, and a latching circuit is created through B1 and B2 contacts, so it stays like that. And so once the temperature drops below 221, it doesn't go back to high flow, it just stays off. So I hope you followed that okay. If not, just play this video back again and go through it. But the takeaway is it's all controlled by relay logic. There's no fancy computer here working all this out. It's just pure relay logic. So don't forget that when you're doing your troubleshooting. Okay, this next slide very quickly, won't take very long, is looking at the eBay cooling system. Now the forward electronics bay is non-pressurized, but we've got a lot of equipment there generating a lot of heat, so we have to have some sort of cooling system. So what we have is 4 fans altogether, 2 internal air recirc fans and 2 exhaust fans. And they basically work in pairs. So 1 recirc fan, 1 exhaust fan, that's 1 pair, and then you've got the other 2 fans for the other pair. The internal recirc fans, they operate continuously as soon as you put power on. The exhaust fans kick in once the temperature rises. So inside the eBay, you've got a series of 4 control switches and 2 over temperature switches. So the 4 temperature control switches control the exhaust fans. So you have 2 switches per fan. Any one switch in its pair that goes above 24 degrees C will cause the exhaust fan to come on. So it is quite possible, although not usual, to have 1 exhaust fan running and not the other one. But from my experience, one single exhaust fan will start, and I can guarantee you within a minute or so the second one will also kick in. So they do work individually, but they will both be running nearly all the time. The over temp switch, they generate a red warning message, electrical bay overheat, if the temperature inside that bay gets to 71 degrees C. So if it gets to 71 degrees C, that's pretty severe, that's pretty hot. You have got some sort of malfunction going on there, and you get the red warning message. So that's the eBay cooling. Okay, almost there now, guys. Just hang in there. So just going to quickly look at the pressurization system. So with a pressurization system, it's controlled by a digital controller, which you can see there with the switches on, the 2 guided switches and the elevation up and down switches, and a little display there showing landing field elevation. So it's controlled digitally in automatic mode. There's also a manual mode as well, where we control the outflow valves directly ourselves. So talking about the digital system first, the automatic system. So on the rear pressure bulkhead, there are 2 outflow valves. One's a pneumatic outflow valve, one's an electro-pneumatic outflow valve. They are linked together, they're slaved together, and when in auto control, the automatic system makes input to the electro-pneumatic outflow valve, and the pneumatic outflow valve will just follow what it's doing. It will mimic it, it's slaved to it. When in the auto mode, basically as we advance the power levers to the takeoff position, it will pre-pressurize the cabin very slightly. We'll look at the cabin schedule in a second. We begin our takeoff run, we go airborne, it goes into the climb mode and basically controls the cabin pressure as we climb, go into the cruise, and then it will sense a aircraft descent and then go into descent mode. The crew previously have set the airfield, that their destination and airfield's altitude in the landing elevation window, so it knows when it's going to land. And what it's aiming for is to descend the cabin and allow, or so that when it touches the ground, we've got a very slight positive pressure at the point of touchdown. So in order to do that, it needs various bits of information. So it gets information from the air data computer. There's a CPAM, which is cabin pressurization acquisition module, which generates the cabin high altitude alarm at 10,000 feet and provides the indications on the ICAS for the cabin altitude, cabin rate, cabin differential pressure. If we go into manual mode, if we want to go into manual mode, we can push the auto manual guarded switch, and now we control the pneumatic outflow valve directly pneumatically. So there's a rotary switch there that controls the pneumatic outflow valve, and we control that directly. And we have to, well, the crew hate it actually. Although you can dispatch the aircraft under the MEL in manual mode, the crew hate it, and I don't blame them. It will basically, for one of the crew members, it's almost a full-time job to monitor that cabin pressure, get it just about right, until they're in the cruise. Once they're in the cruise, it's all, they don't really need to touch it. And then during the descent, again, they're messing around with the controller to get the correct schedule as we descend. The pneumatic valve, outflow valve, and the electro one, they need a vacuum source for it to work. So there's a jet pump which takes air from the bleed system to create a vacuum which allows the outflow valves to open and close. There's a dump switch on there that only works in auto mode and allows the outflow valves to open. Cabin pressure dumps. It dumps at a higher rate than it would normally be scheduled. But within the outflow valves there is a cabin altitude limiter. So it will dump, but it only allows the cabin to dump to cabin altitude of 14,000 feet. And then it tries to maintain it at that. That's enough for the oxygen mask to drop, but it doesn't get too dangerously high. The other thing to point out, if there's a failure with the automatic mode, it's quite possible there will be a fault code displayed in the landing elevation window, which is good. The bad news is, when you go to manual mode, that display disappears, and along with the code. So the crew hopefully will have made a note of that fault code, because once they go to manual mode, it's lost. So a bit of a flaw in the system design there. But that's the pressurization system. There's two pressurization static ports actually at the back of the aeroplane. They provide information or static pressure sensing line to the two outflow valves, and actually not shown on the picture, but they also provide static pressure information to the FADEX as well. They're heated as part of the ice and rain protection system. So here's our cabin pressure information which is displayed on the ICAS screen. That's the center screen all the time. So we've got cabin altitude, cabin delta P, and cabin rate. If it goes out of limits, the digits change from green to red. And this information is coming from the CPAM, the cabin pressure acquisition module. And finally, this is the last slide. So this is our typical schedule. So top picture, it says automatic pressurization and takeoff sequence. So we close the cabin door, advance the power levers to take off, and the pre-pressurization system begins to pressurize the cabin. So the outflow valves and motor closed, and we end up with a 0.2 psi D cabin at a rate of 450 feet per minute. The aircraft takes off and begins a climb sequence, and it holds that original 0.2 psi D for 15 minutes maximum, and then the cabin is allowed to climb in relation to the aircraft rate of climb. Now the aircraft rate of climb, the digital controller is getting that information from the ADC. Once we level off in the cruise, if we're at the max cruise altitude, 37,000 feet, we've got a cabin altitude of 8,000 feet and a cabin differential pressure of about 7.8. Then the aircraft will descend. So again, the controller will sense that from the air data inputs, and it will then descend the cabin as well. We know what time the aircraft, or what altitude the aircraft's going to hit the ground, because we've told it in the landing elevation, which, by the way, they can change at any time if they get a diversion or whatever. So it would descend, and what it's aiming for is to touch down with a very slight positive pressure of 300 feet below our selected altitude. We bring the power levers to idle, and then the aircraft, or the controller, will begin to climb the cabin at a rate of 650 feet a minute. So we're 300 feet below schedule. It's climbing at 650 feet per minute, so approximately 30 seconds, or less than 30 seconds. We'll have, 0 PSID. The outflow valves will be fully open at that stage, and the pressure will be equalized. So by the time we get onto the stand, all the residual pressure should have dissipated. Okay, guys, so that's it. That's air conditioning and pneumatics in a nutshell. So we'll move on to the next chapter.